Why should anyone want to visit country like this? In spite of its beauty, it can be cold and inhospitable, even in the middle of summer. One reason for visiting remote places is to find out more about our environment. On our planet, we are becoming increasingly aware of our interdependence. Not only are nations dependent upon each other's actions, the forces of nature in remote places can also affect or explain happenings much nearer home. A great deal of the work of scientists is highly technical, using expensive equipment and highly trained observers. But within this framework, there are many tasks for the less skilled observer, particularly if he is willing to leave the towns behind and visit the remoter, wilder corners of the world. The British Schools Exploring Society visited North Iceland to undertake survey work in conjunction with Icelandic scientists. Their work was centered on Glufrajökull, one of the largest glaciers in the region. Parts of this glacier have been mapped annually by expeditions of young people from Britain working through the Iceland unit of the Young Explorers Trust. But this was the first time that a complete survey had been undertaken. Since the glacier is many hours' walk from the nearest road, it was necessary to do the survey from a series of camps extending right onto the glacier. The first task in making the map was to establish a baseline on relatively flat country. A special steel tape is laid on the ground between markers. Behind this cloth is a marker for the end of one section and the beginning of the next. The steel tape is stretched and a careful note is made of the tension in it. The influence of temperature is also taken into account. The baseline ends directly under the theodolite. The BSES, which was founded in 1932, has a tremendous fund of expedition experience in remote areas. Every year, a well-organized group of about 70 people, selected from a long list of applicants, sets out on a 6-week expedition. These are some shots taken in 1934, when the Society went to a remote part of Newfoundland. At that time, it was still possible to walk through totally unknown country. These early marches were memorable for the boys taking part, and they were producing observations adding to our knowledge of a few more square miles of the Earth's surface. Today are no less demanding, and quite often you still have to go through country like this. The leader of the 1977 Iceland expedition was Derek Jackson, a veteran of many previous expeditions. Most of the boys came from schools all over Britain, but we also had some from Germany, America, Africa, and Australia. The scientific aims of the expedition included glacier survey and a whole range of other disciplines in which scientists in Iceland and other countries are interested. The geology is particularly interesting, and this, plus all the other scientific work, was led by George Downey, a geologist from Aberdeen University. Most of the rocks are in horizontal layers formed by the eruption of numerous lava flows over hundreds of thousands of years. Ice and water have cut through these layers, so that we have a ready-made section going back through the geological history of Iceland. By studying the nature of these rocks, we can deduce a great deal about earlier conditions in this part of the world. Most of the boys had not much previous experience of geology and very little of working in the field, but thanks to George's expert tuition, they were soon all making a worthwhile contribution to the survey. Later on, they were able to go off in unsupervised groups and do research over a large area hitherto not investigated in detail by geologists. The snout of the glacier itself, where we established an advanced camp. Not the most pleasant of spots for a campsite, but an experienced camper with good equipment should be able to make himself comfortable almost anywhere. Throughout all this work, a high standard of mountain safety has to be maintained. On any young expedition, the leaders are responsible for not only the planning, but also the personal safety of every member. Training, therefore, includes safe movement on ice and practice in emergency procedures. Here they are practicing abseiling on the very steep snout of the glacier. Higher up the glacier, and in less pleasant weather, we practiced other safety techniques. If you're on a rope, it's not so bad, but how about this for free fall? And the same in slow motion, demonstrated by Deputy Leader Bionic Brian Needham. And again. Modern techniques in botany include a certain amount of survey work, and here the botany group are preparing to take transects and sample the plants in the area. A 1 meter square is marked out and a careful sketch is made of all that lies within the area, and all plants are identified. This specimen collection has been prepared to help the non-expert. Despite the bleakness of this land and the fact that snow lies here for 60% of the year, there are over 100 different kinds of plants, some of them very beautiful. Another task was to measure the diameter and therefore the age of these lichen patches. Some are more than 100 years old, and they tell us how long it is since the glacier ice retreated. Weather readings are, of course, an essential background to all our work. Now on to the ice itself. The long poles are to help make a study of ice movement and glacier melting. Modern glacier studies involve working out the mass balance, measuring all the rain and snow that falls on the glacier basin, and comparing this with the amount of water leaving the basin. Sample measurements are taken from points all over the glacier, and these points will be plotted onto the main map by the surveyors. The holes go 2 meters into the ice, and although this looks hard work, you soon become quite skilled at it. The biggest problem is preventing the drill from freezing in. Even then, there's a way of clearing it. Weather readings were taken here for comparison with those taken at the snout of the glacier. Sometimes we took them half-hourly right round the clock to link in with the glacier streamflow measurements. Living on ice and turning out at 2 a.m. doesn't sound much fun, but at least in these latitudes it isn't very dark at night. Going round the stakes in order to take the daily readings. Snow pits had to be dug to find out the snow density at various depths. Small samples of water were taken and later analysed by Dr. Helgi Bjornsson in Reykjavik to find out their deuterium content. The amount of this trace element helps scientists to know how long the water or the ice has remained in the glacier. But most of our work on the water took place in the main meltwater stream coming out from under the snout of the glacier. First, we measured the water depth at the marker post daily, hourly, and sometimes half-hourly round the clock. Unlike normal streams, glacial streams are often high on sunny days, but low on wet days. A more sophisticated way of measuring stream flow is by salt dilution and conductivity. You throw in a measured quantity of salt solution, and then with accurate timing you then measure the reduction in concentration at a point 100 meters downstream. More samples for deuterium measurement were taken from the meltwater stream. The most important scientific task on the expedition was the production of a large-scale map of the whole glacier. Once the baseline had been completed, the survey was extended onto the glacier itself by theodolite readings. The army surveyors trained the boys in the use of these instruments, and soon groups were working independently all over the glacier basin. Once the main points had been fixed by theodolite, plane table mapping could begin. This involved drawing sight lines to all the key features from a number of control stations. The intersections obtained gradually build up to form the map. The Indian clinometer is also used on the plane table, and its function is to indicate vertical angles to surrounding features. Knowing these angles plus the distance enables one to calculate heights and ultimately to put in contours. As we progressed up the glacier, the work of mapping became increasingly hazardous. The early training in safety now proved invaluable. The most important safety asset in country like this is not strength or courage or even great technical knowledge. It is vigilance. You must be alert to the dangers of great crevasses like this one, and the biggest risks could come from carelessness or lack of observation. Fortunately, we were vigilant, and all our work was successfully accomplished. On the hills above the glacier, it is sometimes very cold and bleak. Here, the risks of working on some parts of this glacier are pretty obvious. In the evening, back at the survey camp, the surveyors face the daily task of translating all the theodolite readings into coordinates and building up the first draft map. The end of the expedition is not the day you pack up and go home. A successful scientific expedition has 3 stages. First, the need for the survey must be established. Then the expedition carries out the survey. Thirdly, to be of any lasting value, the results of the survey must be written up and presented. In its scientific work, the BSES works to high standards, and so its results are widely accepted. The Iceland results will be of value to scientists in many countries. Opportunities for young people to share in this kind of work now exist in many groups in Britain, and the Royal Geographical Society is playing an increasing part in assisting young expeditions in many ways. The House of the RGS in London is a focal point for explorers and exploration groups, and includes the headquarters of the British Schools Exploring Society. Lastly, what about the cost of all this? An expedition may seem expensive, but it's good value for money for the scientist who wants results from a remote corner of the world. And it's also good value for money for the youngster who wants to enjoy the experience of a lifetime.